السلام عليكم.
عليكم السلام ورحمة الله وبركاته.
وعليكم السلام ورحمة الله.
صباح الخير، كيف حالكم اليوم؟
الحمد لله بخير يا دكتور.
في مطر ولا في رينز ولا ما في رينز؟
لا والله لا، بس الله يجيب الخير.
الرياض
الله
ما في؟
لا ما في والله.
وجدة؟
والله جدة ما أدري، لكن الرياض الآن جوا يعني اعتيادية، ما في لا برد لا غيوم لا.
هنا كمان يعني كويسة، بس هم قالوا إنه في توقعات وكده، ربنا ييسر إن شاء الله. أوكي
جيب الخير دكتور، جيب الخير.
الله يبارك لك، المطر كويس الحمد لله. Okay, شباب, today we are going to consider our last chapter in this course, and this is chemical reactions. Chemical reactions, this is what you know, you burn carbon, you burn fuel with air to get energy, to make other processes. So this is chemical reaction. When you burn carbon with oxygen to get CO2, this is what we call chemical reaction. And you have passed through that. So let me see what are the applications of that. In power production, you remember we have boilers, we have gas turbines, and we have aircrafts, we have internal combustion engine. All of these require fuel. If you remember, we have steam power plants, and you have already a project on that. And we talked about energy or fuel needed to burn to get energy for steam production. So we are talking about the boiler. I don't know what to name. Okay, we talked about the boiler in the steam power plant. The boiler produces steam, but it needs to burn fuel to get energy to have the latent heat for the steam and superheating. Also in gas turbine, we have part of it as called the combustor, compressor, then combustor. So in the combustor here, in the combustion chamber, then you add fuel to that. Also in aircrafts, we have to have fuel. Internal combustion engine, we have to go to the gas station to fill that. So all of this here depend on chemical action. Also, if we go to the process industry, when you have steel, look at how do we get the steels formed. We melt the steel by gases, by fuel combustion, and then we shape it either into cylinders, into plates, into angles, whatever. This is the same. Also for the glass here, what we do here is to melt the glass and then we shape it to different, to cups, vases, anything like that. Then in domestics at home, you use fuel in oven for cooking, for heating, and so on. Also, the next one is firefighting. When you have a fire in your next home, you want to stop this fire before it comes to your house. So this is what we call here firefighting, extinction of fire. Okay, so these are all applications here. And I promise here I can drop this chapter and we finish the course. If you go without this, if you go without gas turbine, without steam power plants, without any electricity, without air conditioning, no aircrafts, no automobiles, you do not have steel, glass, you do not use ovens, you cannot use firefighting. So it is in all our life now. All of our life is depending on fuel combustion chemical reaction. And this is the importance of this chapter here, although it is the last chapter, but as you see here, it is very important. It goes to every part of our life. Okay, what do we want from this chapter? What we are looking for? Okay, let me look at this here. This is what we call the heat engine, which we applied in thermal power plants or in gas turbines and internal combustion engine. And then we add heat and then get work, and there's a QL to satisfy the second Luxembourg dynamics. And we have already calculated the cycle efficiency W over QH. So this you are quite familiar with in our previous chapters. Now, where do we get the heat from? Do we go to the gas station and ask him kindly, please give me 10 megawatt, 10 megajoule, or this is not the case. But you go and ask him, I need 10 liters of gasoline. So you ask for fuel. So what we actually have here is what we call a cycle efficiency. But when we consider the real things that we have to add fuel here, and therefore this is what we call the plant efficiency. So this is the plant here. When you talk about an automobile, then this is not present in the automobile. This is a cycle here that runs that. But when you present the automobile, you have to consider the fuel that you add to that. So now what is the situation now? The situation, we talk about efficiency. And the efficiency, the work is the output, yes. But the energy added is not QH. It is actually the energy in the fuel. When you go and buy 10 liters of gasoline, you know that you have about 400 megajoule in this 10 liters. And therefore, we divide here by the energy released from this fuel. So now we are going to move from the view here, that's the cycle view, to the plant view. So this is the real engine here. The real engine here is that we have fuel here. What's the difference here? When you burn this fuel, there is a combustion process here, which we are talking about in this chapter. This combustion here will tell you how much energy you can get from this fuel. And you know that when you burn the combustion, there is a carbon monoxide goes out, some other fuel may not burn. So this is an efficiency here. And this efficiency, we used to call it 100% in the past, because we consider all the energy in the fuel goes to heat. This is not the fact here. So now we are going to move from this simple cycles, this is a cycle efficiency, to the plant efficiency. The difference is that what we divide before here. We divide here by QH. No, we are going to see what is the energy released from this fuel. So you have in the, once you buy 10 liters of gasoline, there is an energy there. This energy, how do you consume it here? This is the issue that one. Okay, so this is the view here. We have this now. We want to add this part, such that we'll be considering the plant efficiency or the internal combustion efficiency, the automobile efficiency. Okay, what do we need from this chapter? We have 3 steps, as a matter of fact. Here. The first step here, we have a fuel reaction here. For example, carbon plus oxygen will give us CO2, or hydrogen plus oxygen will give us H2O. So we need to write the equations. We need to learn how to write the equation. This is the first part. If I have any question in an exam, it will be part A. So part A will be write the reaction equation, which is H2 plus half O2 will give us H2O and so on. The second here is that when we burn fuel, we need air. We take air from the atmosphere. So I need to calculate the air to fuel ratio. So this is the second step. A is calculate, write the reaction equation. B in the question will be the air, calculate the air to fuel ratio. Third, what is the energy released from this fuel here? How much energy released? This will be based on how much air you add and how much unburned combustion, unburned fuel, all of this here. So we need to know here how much energy released from the fuel. All right. So this is our view. This is what I need at the end of the chapter. Just imagine any problem now we have in an exam. Part A, this is a must here. And should not do any mistake in that. Part A, write the reaction equation. Part B, calculate the air to fuel ratio. Part C, calculate the energy release. And this energy release will be used in this part. So we are completing the cycle that we have before by adding this part here as the combustion. All right, Shabab, is it clear here, the applications and overview of what we are going to cover at the end of the chapter?
Yes.
Any questions, Shabab? Okay, it's very important to know where are we heading. Okay, so we know this is at the end here, we have 3 questions, A, B, C. A, calculate, write the reaction equation. B, what's the air to fuel ratio? C is the energy, what's the energy release? All right. So just a little bit in details here, we will apply the conservation of mass to reacting system, and we apply the energy balance to the reacting system, and then also we need to determine what is the adiabatic flame temperature, what is the temperature for a flame. When you see a flame, when you see a fire, what is the temperature of that? And this part, second law, this will be omitted from our analysis in this course. So we are not going to consider more details in the second law of the combustion process. Okay, so this is the equation I'm talking about here. This is what we call a reaction equation. So this is we have fuels and combustion. So this is CH4 will burn plus will need oxygen, and this will give us CO2 plus H2. This is the reaction equation. The first thing we will need here is to balance this equation. To balance this equation for 1 kilomole of CH4, how much kilomoles here, how much kilomoles here, how much kilomoles here. So you need to write correctly the reaction equation. So this one issue that we have. We have fuels, we have different fuels, and these different fuels, it can be gasoline, it can be light diesel, heavy fuel. We call this, all of this here, we call it hydrocarbon fuels, because all of them have part of carbon and part of hydrogen. So this is methane, for example, octane, carbon and hydrogen, and therefore we normally, in general, we call it CnHm. So n number of moles of carbon plus m number of moles of hydrogen. And all of these here come from refining the crude oil. You get gasoline, kerosene, oil fuels, and so on. So this goes from heavier, lighter to heavier fuel. And it gives you here the energy content per liter. You remember we used this in the past. Those who made the project extension for the project, they utilize this amounts here, how much energy per liter. So this we can get here from the literature. But in this chapter, we are going to calculate these values. We are going to calculate this here. And this tells you how much equivalent of gasoline. So you can see that the light diesel or heavy diesel have less energy content per liter in terms with regard to gasoline. And for example, liquefied natural gas here has more. And then, for example, this is 1.55. And this compressed natural gas per liter, it is 3-4 times the energy in the gasoline. Okay, so this is here. We are going to use, these are the types of fuel, all with CnHm. N is 1, M is 4, this will be methane. N is 8, H18, this will be octane, and so on. Okay, then to burn with oxygen, of course, we do not burn with oxygen all the time. As a matter of fact, when you burn with air. And therefore, we have to consider the composition of air. In each mole of air, in each 1 meter cube for air, we have 21% oxygen and 79% nitrogen. And this means that when you have, if you have 1 kilomole of oxygen, you have to take with it 3.76 nitrogen. Okay, now I burn here with oxygen. And to get oxygen from air, you have to take air. When you put in the engine of the car, it takes air. How much oxygen is that? 21%. And this means when you consider 1 kilomole of oxygen here, automatically you have to take 3.76. Where do you get 3.76? It is 79/21. So when you have 1 kilomole of oxygen, you have to have 3.76 kilomole of nitrogen with it. So in the reaction here, it's not oxygen, it has to be oxygen plus nitrogen. For each 1 mole here, you have 3.76 kilomole of nitrogen. Okay, so this is the nature of air, because we do not burn with oxygen, or we burn with oxygen, but we take air, and therefore an extra amount has to be there, which is nitrogen. So nitrogen is coming anyway, it does not react, it goes in and it goes out. But we have to know now that for each kilomole of oxygen, you have to get with that 3.76 of kilomole, and means that you have already, to get 1 kilomole of oxygen, you have to take 4.76 kilomole of air. So this is regarding oxygen and air. All right, let us look at the reaction equation now. This is a reaction equation. C plus O2 will give us CO2. H2 plus O2 will give us H2. And this has to be balanced. This is number 1, A part, and no mistakes in that. Because this is a must. At the beginning of any problem, we have to write the reaction equation. And I'm sure that you can write the reaction equation correct. But the problem is that no errors, because any error here will come to part P, will come to part C. And therefore, let us look at that here. See here, this is the part we call it reactants. And this we call it the products. Let us read this equation. What does this equation mean? It means that I have 1 kilomole of carbon will burn with 1 kilomole of oxygen to give us 1 kilomole of carbon dioxide. The carbon has to be balanced here. So I have 1 carbon, this is 1 carbon. This 1 oxygen, O2, this 1 O2. So this 1 molecule, or you can say 2 atoms. So 2 atoms here has to be 2 atoms there. This is the balance is the equation. If I go here, this is hydrogen, H2, plus O2 will give us H2O. Now hydrogen will require, gets hydrogen, water will be H2O. And therefore I take half of this only. So this has to be H2, 2 atoms here. Or 1 mole, it's 1 mole. Here, 1 atom or half a mole. So this would be also half a mole or 1 atom it is all. So this is balanced equation. Please, no mistake in that. I'm sure that you are capable of doing it. You are expert in doing that, but we have to be careful, no mistakes, because this will affect the other parts for the problem. All right, let us go more now. So now when I have a fuel, this fuel will burn with air, and then combustion process, combustion chamber here, and then we have heat transfer. Okay, we write heat transfer as the heat added. So when we write the equation, we say this is heat added. But in most of our reactions, this will be out of the system. So we put it in, but it will come at the end as Q is equal to minus that. Then the products here, carbon will burn CO2. Hydrogen will burn to H2O. And then we have air here, nitrogen will come as same as nitrogen. So this is, we call it complete combustion. Why complete combustion here? Because there is nothing can burn anymore here. So this is CO2 cannot burn anymore. H2O cannot burn anymore. Nitrogen also the same. So this is what we call complete combustion. We will come back to the same. Examples of hydrocarbon, this CNHM can be methane, octane, or can be a mixture, carbon, hydrogen, sulfur, oxygen, nitrogen, and so on. So this is a typical combustion chamber that we have, and therefore this is what we are going to study in the next parts. Okay, so this is a combustion, and introducing the combustion here, we say here this is in combustion, we have rapid oxidation of combustible elements of the fuel results in energy released as combustion products are formed. The 3 major combustible elements, one is carbon, the second is hydrogen, and sulfur. This mostly will find this in a fuel. So when you have a fuel, carbon and hydrogen definitely will be there. Sulfur, you may find some part of sulfur in the reactants. Okay, so we say here, we define combustion is complete. When we say combustion is complete means what? Means that all carbon is burned to carbon dioxide. All hydrogen is burned to water vapor. All sulfur is burned, if there is sulfur, it will burn to sulfur dioxide. So this is what we call here fully complete combustion. In some cases, you do not have complete combustion, you have incomplete combustion. For example, some of the carbon will burn to carbon monoxide. If you find carbon monoxide in the exhaust, means that this is incomplete combustion. Therefore, because carbon monoxide still can burn outside the engine. Okay, so this is here is 2 examples I have mentioned here. So let us read this again. This means that 1 kilomole of carbon plus 1 kilomole of hydrogen, of oxygen, will burn to give us 1 kilomole of CO2. Okay, this is by volume. All the time is by volume, mole. We can say also, in terms of mass, I can say that 12 kilogram of carbon. Where did I get the 12 here? Because the molecular weight of carbon is 12, plus 32 of oxygen, which, because the molecular weight of oxygen, moles of oxygen, is 32. So this is 12 kilogram of carbon plus 32 kilogram of oxygen will give us here 44 of CO2. So this is balance the equation here. You also note that the mass is balanced. 12 plus 32 is equal to 44. So this is how do we write the equation here. Okay, let us take an example here. Okay, how do you write the equation? Now I'm burning CH4. Okay. This is the way I do it, as a matter of fact. But this is here is done in another way here. So you can say that CH4 will give you CO2. Forget about the red parts here. CH4 will give you CO2. So you put CO2 here. CH4, hydrogen will burn to H2. So you put H2O here. This is the first thing. You see what are the products of that. Don't balance now. Don't put A, B, C. But you have carbon will burn to CO2. Hydrogen will burn to H2O. Then you start balancing here. That C here, so B here will be equal to 1. Based on the balance of carbon, this will be 1. Balance of hydrogen, this will give you C will be 2. So now I can say here C, this C here, because this has to be 4 to have this, so this will be 2. Then normally do that. Carbon first, hydrogen second, leave the oxygen to the end. Then oxygen I have here, you can count based on moles or based on atoms. I normally like moles. So I have P here as, this is here, I have O2 here, and then I have, so this is now 1, so this will be 1, plus here C is 2, so this is another 1. So I have 1 mole here and 1 mole here, so this will be 2. Or if you can put it A, B, C, and then you apply the balance here like that. So it's up to you. You can say from the balance, A, B is 1. From the balance, H equal 4 here, so this will be 2C. From the balance here, 2A will be equal to, it's talking about atoms now, 2A will be equal to 2B plus C. So this will give you that. Then we find here that C will be equal to 2, and then B is equal to 1, and then you get A from that here, from this balance, it will be 2. Okay, Shabab, I need this to be 100%. If you want to repeat this 5 times, I will.
والله ما هو.
ما واضحة. Okay. Right. Okay. Now we write the equation like that. I need to write this equation. Okay. So now start by putting CH4 here. Okay. Then I go to the other side. I put an arrow here, and then I go to the other side. Carbon will burn to CO2. So you write just CO2 here. Hydrogen will burn to H2O. So you write just H2O here. Then, of course, we need oxygen. So put oxygen here, O2. Then put this as A, B, C. These are unknowns now. Then, to get A, B, C, then we balance here. We start by the carbon. Balance the carbon. Here on the left-hand side, I have 1 carbon. On the right-hand side, I have B. So I put B here. So this will give me B is equal to 1. So I can put here, I can put 1 here. Then look at the hydrogen. Hydrogen, I have 4 on the left-hand side. On the right-hand side, I have 2C. So I put 2C. So C will become as 2. So now I put here C as 2. So I put here 2 in this. Then balance the oxygen. I have here 2A and 2A atoms. So this will be 2A. Here this will be also 2B plus 1C. So this will be that. Then I put B here is 1, and I put C here as 2. So this will give me, divide by 4 by 2. So this will give me 2 here. 2B will be equal to 2 plus C, which is 2. So this is 4 over 2. So A will be equal to 2. So we write this is the final answer here now. You start by putting CH4 with 1 here. This is based on 1 kilomole. You put CO2 here, you put H2O here. Then you put A, B, C, and then you balance the equation. Okay, Faisal?
واضحة الحين، واضحة الوزن واضح. بس عندي سؤال دكتور.
Sure, please go ahead.
كيف أعرف النواتج أنها CO2 وماء H2O؟ لا
Yeah, okay, divide it to this. C will burn to what? It will burn CO2. Hydrogen will burn to H2O. So this is coming from the previous one here that we have written. This one here. So this is here. This is well known. The H2 plus O. The H2 will burn and give you H2O. Of course, it can be HO H2O2, any other than, but this is a stable value. Hydrogen will burn into water vapor, and then carbon will burn into CO2. This has to be known first, all right? This is why we take chemistry, so this has to be known. This is the only two here, in addition to this, all what we are going to face. Carbon and hydrogen, because we're talking about carbon and hydrogen. So if you do not know that, خلاص, you know it now. Carbon will burn CO2, hydrogen will burn to H2. We only have some others like sulfur. Sulfur will burn into what? Can anyone answer me? If I write the equation for sulfur, if I replace carbon by sulfur, S plus O2 will give us what?
Sulfur.
Yeah, it will give me SO2. Right?
Yes.
Okay, I think as far as I remember, there is no others here. So C will burn CO2, hydrogen will burn to H2O. This is the main, most of our equation, 99% will be those two equations here. So first of all, you do not have to know other than these two equations here. So it's already known now that carbon will burn to CO2, hydrogen will burn to H2O. خلاص, this is known now, and then we do not have any other fuels, only maybe sulfur sometime. So this is the equation. We'll come to more examples here. So this is another example here. A complete combustion of octane. So say complete combustion. Complete combustion, this is why you see here CO2 and H2O. This is a complete combustion. If you see carbon monoxide here, this is not complete combustion. So when you say complete combustion, this has to be CO2, this has to be H2O, there is no CO here. And this is octane, so octane you get the formula from the tables or maybe given the problem. The balanced, write the balanced equation. I need you to know this here. And let us make it together now without going to the solution. If I have CH8, CH8H18, this is what I do. Step 1, I write here, so I put O2 here, and then I have arrow, and I put CO2 here. Forget about A, B, C, A, B, D here. Then hydrogen will burn into H2O. Then I put H2O here. Then I go here, the next step, I see this is 8. Then what will be this value?
8.
8.
8. This is a balance. Then what is this value will be?
18.
18 over 2. Right?
Yes.
Yes.
Yes. 9.
18 over 2, so this will give me 9. Then
Yes.
I calculate the oxygen. Let us calculate the oxygen. How much is A now? So now we'll go to this here. How much is A? Here is 8, right? Plus how much here?
9.
No, not 9, because this is atom. Either you count atoms or moles. I like to call it moles, so make it always O2. So I have 8 O2 here plus 9 over 2 O2. All right, Shabab, I want to do this again.
Yes.
This is the
Yes.
equation here. You write this from chemistry or from what we learned here. Carbon will burn to CO2. Hydrogen will burn to H2O. Then balance carbon will give you B, it will be 8. Balance the hydrogen, this is 2D. I look at atoms here. How many atoms? I have D. How many atoms here? 9, because atom is H2. So I have 9 here, so I put 9 here. Then the oxygen. Count the atoms. Atoms, this is 8 here. How many atoms here? 9 over 2. Atom means it's how many O2, not O. So it's 9 over 2 plus, so this is 4.5 plus 8, this will be 12.5. All right, Shabab, I know it is simple, just need little practice, and I have no problem with that other than students and silly mistakes, division here or something like that. But I have no problem with the students except maybe 1 or 2 did not exercise. But if you do exercising, it is easy for you to do that. So now we write this as C8H18 plus 12.5 plus will give you this equation. But my problem now here is that there has to be no mistakes. Shabab, I'm repeating this again. No mistakes here. Why no mistakes? Because this is A, will affect part B when you get the H ratio. It will affect, you will use this also in calculating the energy released. So there is no mistakes in that, please. All right. Okay. Now I want to say two things here. this equation is based on what? Is based on burning 1 kilomole. So we have 1 here. So you assumed that you have 1 kilomole and you base the equation on that. So this is equation is based on burning of 1 kilomole of octane. Okay, the second thing is that here, when you have in your engine, where do you get air or oxygen? You don't you buy fuel and you put it. And then do you buy oxygen? As a matter of fact, no. And therefore, we have to write here to place this as air, not oxygen. Because in fact, what goes to the engine is air. So now we have to add the nitrogen here. The nitrogen will go to the equation. Of course, when you balance the equation, nitrogen does not appear here because nitrogen in will be equal to nitrogen out. So this is fine here. When you balance as masses, then in this case you may not write the nitrogen. But when you consider energy, then you have to write the nitrogen. Why? Because the nitrogen here will go at room temperature, but it will go from the combustion at a high temperature. So the nitrogen will take energy and throw it to the atmosphere. And therefore, now we cannot write the equation like that, but we have to translate this in terms of air. How to translate this? CH4, so this will stay as is now. Every 12.5 oxygen, every 1 kilomole of oxygen, you will get with it 3.76 because this is the ratio here. For each 21, you have 79 nitrogen. For each 21 oxygen, you will get 79 kilomoles of nitrogen. And therefore, for 1 mole of oxygen, automatically you will have to have 3.76. So 1 mole of oxygen will have 3.76 nitrogen. This has to be. Okay, so now this is air now. Okay, this is air now. So this is we rewrite the equation here to this one, but you're adding nitrogen. The nitrogen will go as exit as is this one. So 12.5 multiplied by 3.76 will give you the value here as that. Okay, so now we have 2 steps. One is to write this equation as we have seen in the previous slide. The second thing is that to add the nitrogen. How much? So once I write this, just I open a bracket here and then write 102 plus 3.76 nitrogen. This will remain as is here. All right, so this is translating the equation. Instead of oxygen, we have to have air because this is the actual life we burn with air, not oxygen. All right, so this is here. Let me go to this. Okay, so this is regarding the equations. All right, Shabab. Okay, 2 things I need from you here. Okay, those 1 slide, second slide, 3 slides. Okay, this has to be made 100% correct. So just go today and write for this fuel. You'll find many examples on the internet, in the book, and so on. Other different fuels. So we made it here for methane. We made it here for octane. You can make it for any other fuel. Okay. Shabab. So this here, no mistakes. And then once you write this, then put a bracket here, like this, and then add to oxygen 3.76 nitrogen, and then balance the nitrogen comes here. This is a complete combustion. So this is writing now the complete combustion equation for 1 kilomole of octane. And this is burned with air. All right, so this is what we have mentioned now is how to write the reaction equation. This part A of any question, no mistakes. All right, no mistakes, Shabab. All right, okay. So now I need you to go home today and look at the internet, open your mobile, whatever, go to the book and solve as many examples to write the reaction equation for complete combustion. Okay, so this is the first part that I want to cover in this chapter. The second part is what is the air to fuel ratio? Okay. What do you read in the car? Do you read the amount of fuel or not? You have a dial for the fuel. You know how much fuel you use. You can see the dial there. But do you read the air? We never read the air that's going to the engine. So there is a carburetor or fuel injection that takes a certain amount of air with the fuel. But let me ask you, how much air you take for the fuel in kilograms, I mean in a mass ratio. For each 1 kilogram of fuel, how much air that the engine takes? Any idea? So now you get 10 liters of gasoline. Suppose this 10 liter is about 10 kilogram. How much is this when you move from here to Dammam, you finish this 10 kilogram of fuel? How much air went to the engine?
Depends on the type of fuel.
All right, depends on type of fuel and the type, that's fine, that's good. But how much? Give me a value. It is 1 to 1, mass of air to the mass of fuel is 1 to 1, or 100 to 1, or what? Approximately. Anyone looked in his mobiles and internet? Okay, so now normally we talk about here around 20 mass of air over 1 kilogram of fuel. So every 1 kilogram of fuel takes about 20. This is, as you mentioned here, you are correct 100%. That depends on the fuel. It depends on the mixing. It depends on so many things here. But I can say it goes from 15 to 30 maximum. So this is here, every kilogram fuel needs from 15 to around 25 or a little bit more of air. And we need to calculate this here. But let us just say a definition here. So air to fuel ratio by definition here is the mass of air over the mass of fuel. So when I have here 1 kilogram of fuel, and then I have, he's already giving an answer here. This 1 kilogram of fuel takes 17 kilogram of air, and the products will be 18 products. So we can say that the air to fuel ratio is 18. And this is by mass, All right, sometimes we say here also by mole. So I see how many moles in air, how many moles of fuel. I divide, I get this is the air to fuel ratio. But by default, if someone asks you what's the air to fuel ratio, it has to be by mass. Okay, so this is by default. It is the mass of air over the mass of fuel. If he asks you per mole, then you see how many moles of air and how many moles of fuel, and divide them. So we have this is here on a mole basis, moles of air over moles of fuel. On a mass basis, mass of air on a mass of fuel. How can we translate both of them? Mass of air will be equal to the mass of the mole of air multiplied by the molecular weight of air, which is 29. So if I multiply number of moles by 29, this will give me the mass of air. Then the moles of fuel, if I multiply it by the molecular weight of fuel, this will give me the mass of fuel. So I can translate this one to the other one. So I can change from air to fuel ratio on a mole to air to fuel ratio on a mass by multiplying the molecular weight. If I have the air to fuel ratio by mass, I can divide by the molecular weight, I get that. All right, so this is the ratio here. So this is if you have this, you just multiply by mass molecular weight of air, which is 29, molecular weight of fuel. If it is methane, for example, this would be 16. So you get the air to fuel ratio by mass. So this is by definition here of how to define the air to fuel ratio. Sometimes we use what we call fuel air ratio, means that it is a reciprocal of that. It is here mass of fuel over mass of air. So most of the time we use air to fuel ratio, and the default is mass. And sometimes we use the air to fuel ratio by mole. Sometimes also we use fuel to air ratio. So in this case, it will be 1 over 20 or 5%. This is the fuel to air ratio. Okay. So now let us say here that we define here the theoretical, we define a word that's called theoretical mass of air. Okay. Theoretical mass of air is, let me just go from here. Okay, the theoretical amount of air is the minimum amount of air that supplies sufficient oxygen for the complete combustion of all carbon. So now let me ask you here, is this theoretical air or not? To answer this, look at this here. Is this is a complete combustion?
Yes.
Okay, it's complete combustion. So we satisfy that. Is it the minimum amount of air? Yes, because there is no extra air here. There is no extra air here. So this is here satisfies both of this. It is complete combustion and it is the minimum amount of air. So we call this here, this amount here is the theoretical amount of air that's needed here. Of course, do we use this in practice in the engines? Is this suitable for the engine or not?
I think no.
I think you are right. That's no. Why no? Because I add more air to make sure that you burn the fuel. You cannot add the exact air and the exact fuel in a combustion chamber. Of course, they may not mix together, and therefore you may find fuel here. Because the fuel is costly, the air is free, and therefore we have to add more air here, such that I make sure that I burn all the fuel. So in practice, normally we have extra air, and this is why we are defining now theoretical amount of air. But this is of course not practical to use in engines. So we have to use more air to make sure that we burn the fuel. Okay. So this is what we call theoretical air. Theoretical air is the amount. So when you write the equation like that, with complete combustion, means that you have CO2, H2O, no carbon monoxide, no hydrogen here, no CH, any components of the fuel, then this is complete combustion. Then, if you do not have any extra air here, means that this is the minimum amount of air. If you write the equation like that, then this is what called here is the theoretical amount of air. So this is a definition here. So for complete combustion, you have to have CO2, H2O, and CO2. Then, and of course, no free oxygen appears because we are talking about minimum here. And therefore, this is normally called the theoretical air. But it says normally here, we add more air. Okay, so now we can say here, if we add more air here, 50%, so I say I have 150% of the theoretical air. Or I can call it excess air. So suppose this is the theoretical air. As we agreed that I have to add more air here. So if I add 50% more air, so I say here, this is the air here will be 150% of the theoretical air. Or I can say this is 50% excess air. Okay, so this is how to define the theoretical air. Okay, so now let us have this here as this equation. So now exploring the combustion concept. Now I want here to go back and write this equation. Okay, so this is another exercise here. Okay, CH4 will burn into what? I'm just writing the equation now. Don't look at the numbers here. So CH4 will burn to CO2. I just write CO2 here. H4 will burn to H2O. Then I write that. Then I balance the carbon. So here, this is 1, so this will be 1. I balance the hydrogen. How much hydrogen? I have 4 here. So this will be 2H2. So I balance this. I got 2, and I got this 1 here. Then we balance the oxygen. How much oxygen? How many oxygen now? I have 1 atom here, and also 1 atom here. Because this, I'm sorry. I have 1 kilomole here and 1 kilomole here. Or 2 atoms here and 2 atoms here. So this is here. I have 1 atom plus 1 atom. So this will give me 2 here. Then I open this brackets, and then I add 3.76 here. Then I get the nitrogen, 2 multiplied by 3.76 will give me that. So the balance, this is balance is the equation. If you do not want to do this way, just write A, B, C, D here, and balance the carbon, get an equation, gets this value, balance the equation for hydrogen, gets this value, balance the equation for oxygen, gets this value, and then multiply by this to get the nitrogen. It's up to you, but this has to be 100% Shabab. Okay, we do it here. Okay, if I write the equation, I write CH4, so I write CO2, hydrogen will burn to H2O. Then balance the carbon, balance the hydrogen, then balance the oxygen. I have 2 components here, so balance the oxygen. Then just paste this bracket here, and then get the amount of atoms for nitrogen. So this is how to write the equation. I don't want any mistakes here, and then I will leave you at this point, and then we'll complete next time. Okay. So what is the duty today? Let me see what is the exergy. How many of you are going to make this? To practice at least 3 types of fuel. Shabab, can you raise your hands? I need 31 hands. Shabab. I have only one, Mansoor, Hussein. I have not so many, huh? Okay, Yazid. This is a low exergy, يا شباب.
at the end of the process.
Okay, inshallah. So I promise me to have at least write 3 equations. Why I'm saying this? Because you remember we sometimes have problem with the instructor. Say here, I made a mistake in this part and it affects all other parts. So this is why this has to be 100% because it will affect the other parts. Part A in any question in this chapter will be write the reaction equation. Okay, Shabab. So let me take attendance and then you can, so I already downloaded attendance. Okay. Any questions, Shabab? If you want to leave, you can leave for the other class. If you want to have a question. Yazid is raising his hand because he's going to make this, or you have a question? I see.
لا اساس بسويها نسيت انزلها.
Why is Khalid says, did anyone invite Khalid? Because he wrote a message here. I don't know when was that. This was 9. I hope he's there, huh? Khalid, did you attend? Khalid Al-Hamdan. Okay, خلاص. Okay. طيب يا شباب, any questions? Okay, so I'll see you inshallah Sunday. I expect to finalize this by the end of the next week or early. So I promise, I know that I owe you 1 class, a makeup class for midterm. So I promise I'll give you 1 off, maybe 2 offs. So we will see inshallah. But next week, hopefully we can finish this chapter inshallah.
Inshallah, thank you.
جزاكم الله خير. See you on Sunday inshallah. Have a nice weekend. Hassan Filimban here. He invited me
Yep.
for a talk. Thank you, Hassan, for inviting me for a talk. Did you invite your fellows here or not?
Yes, I invited them.
Yeah, okay.
دكتور
نعم.
عندي كومنت بسيط عن هوموركس
Yes.
إذا ما تمعنا.
Please go ahead.
أنا عندي في الهومورك الأول إني أنا ما سلمت، رجعت للإسكانات اللي سويتها لقيت إني مسويها في 9 سبتمبر، فمتأكد إني أرسلتها وجاني إني ما صمت.
طب هي موجودة هنا. طيب this is a problem I found with some students. So let us solve this in office hours. So I can open your the blackboard and we can look at that. Okay, so how about office hour on Sunday, inshallah, or Tuesday? If this is not suitable for you, if it's not suitable for you, just let me know so we can have it before 6:30 or after 6:30.
أي وقت إن شاء الله.
خلاص إن شاء الله. Sunday or Tuesday at 6:30. This is the normal office hours that we have. So we can look this in details إن شاء الله.
إن شاء الله. يعطيك العافية.
أهلا بك. يا ريت والله.